Hello and welcome. Get comfortable. Pull up your blanket, adjust your pillow, and let yourself settle in. Tonight, we're going on a gentle journey through space, not to anywhere frightening or chaotic, but to one of the universe's most misunderstood and surprisingly peaceful phenomena: black holes. Now, I know what you might be thinking. Black holes? For relaxation? But trust me, once you really get to know them, black holes aren't the cosmic monsters they're often made out to be. They're more like the universe's quiet guardians, ancient storytellers, and patient architects of galaxies. They're places where time slows down, where the rules of reality bend in the most beautiful ways, and where the universe reveals some of its deepest secrets. So close your eyes if you'd like, or let them rest gently on a point in the distance. Breathe slowly, and let's drift together into the calm, mysterious world of black holes. The gentle nature of distance. Here's our first comforting fact. Black holes are really far away. The nearest known black hole to Earth is about 1,600 light years away. To put that in perspective, if you could travel at the speed of light, the fastest speed possible in our universe, it would still take you 1,600 years to reach it. In human terms, that's incomprehensibly distant, unimaginably remote. You could live 1,000 lifetimes and never even come close. So as you lie here tonight, you can rest easy knowing that black holes exist in a part of space so far removed from our daily lives that they might as well be in another universe entirely. They're not lurking around the corner. They're not hiding behind the moon. They're out there in the deep, dark velvet of space, minding their own business, doing what they've been doing for millions or even billions of years, quietly existing, patiently waiting, peacefully spinning in the cosmic darkness. And think about this for a moment. Space is so vast that even though there are millions of black holes in our galaxy alone, the chances of ever encountering one are essentially zero. The Milky Way galaxy is about 100,000 light years across. That's a disk of space so enormous that if you scaled it down to the size of North America, our entire solar system would be smaller than a grain of sand. Within that vast expanse, those millions of black holes are scattered like distant lighthouses, each one minding its own business, each one separated from its neighbors by gulfs of empty space that dwarf anything we can comprehend here on Earth. So rest easy. The universe has given us plenty of room. Black holes exist in their realm, and we exist in ours, separated by distances so vast they're almost meaningless to contemplate. Black holes are mostly empty space. Here's something wonderfully paradoxical about black holes. Despite their incredible density, they're mostly empty, just like everything else in the universe, really. You see, a black hole's edge, what we call the event horizon, can be enormous. Some supermassive black holes have event horizons larger than our entire solar system. Imagine a sphere that could contain the Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, and all the space between them. That's how large some black holes are. But all of that mass, all of that gravity, is compressed down into an infinitesimally small point at the very center called the singularity. So if you imagine a black hole as a sphere, the vast majority of the space inside that sphere is just empty space-time, curved and twisted in fascinating ways, but empty nonetheless. It's like a cosmic snow globe, mostly space, with something mysterious at the center. This emptiness is part of what makes black holes so peaceful to contemplate. They're not crowded, chaotic places. They're vast, quiet expanses where space itself stretches out in ways we're only beginning to understand. In fact, if you were somehow able to observe the interior of a black hole, which you can't, because nothing can send information back out once it crosses the event horizon, you would find it to be one of the loneliest places imaginable. Just empty space-time, curving endlessly inward, silent and still. There's something almost meditative about that image. A vast, quiet emptiness, a place where the usual chaos and noise of the universe falls away into profound silence and solitude. The sound of silence and the deepest note. In space, as the old saying goes, no one can hear you scream. And nowhere is this more true than near a black hole. The vacuum of space around a black hole is one of the quietest places in the universe. No air means no sound waves, and without sound waves, there's nothing to hear but the profound silence of the cosmos. But here's where it gets interesting. In 2003, NASA discovered something remarkable. Using the Chandra X-ray Observatory, they detected sound waves coming from a black hole in the Perseus galaxy cluster. Not that you could hear them with human ears, the note is about 57 octaves below middle C, far deeper than any sound humans can perceive. To put that in perspective, the deepest note a piano can play is about 27 hertz. The deepest note a human can hear is around 20 hertz. The note from this black hole is about 10 million billion times deeper. It's been resonating through space for about 2.5 billion years. A cosmic hum so low and slow that it's less like music and more like the universe breathing. Imagine that. A sound so deep, so slow, so patient, that it's been playing the same note since before complex life existed on Earth. When this note began, our planet was inhabited only by single-celled organisms. No plants, no animals, just simple life in ancient oceans. While out in space, this black hole began its endless song. That note has continued uninterrupted through the entire history of complex life on Earth. It hummed through the age of the dinosaurs. It resonated through the ice ages. It continued while humans evolved, built civilizations, and looked up at the stars wondering what was out there. And it's still playing now, as you lie here in your bed, preparing for sleep. Somewhere in the Perseus galaxy cluster, 250 million light-years away, that same note continues its slow, patient resonance. There's something profoundly peaceful about that, isn't there? The universe, humming to itself in the darkness. A song so long and slow that human lifetimes are like individual heartbeats within it. It reminds us that there are rhythms in the cosmos far slower and deeper than anything we experience in our daily lives. Time moves differently there. One of the most beautiful and mind-bending aspects of black holes is how they affect time. According to Einstein's theory of relativity, the stronger the gravity, the slower time moves. And near a black hole, gravity is about as strong as it gets. If you could somehow safely observe someone approaching a black hole's event horizon, you would see them move slower and slower from your perspective. Their movements would become languid, dreamlike. They would appear to be moving through thick honey, each gesture taking longer and longer. Eventually, they would appear to almost freeze in place, their image getting dimmer and redder as time itself stretched out for them. From their perspective, though, everything would seem normal. Time would pass at a regular pace for them, but the universe outside would speed up. They could watch stars being born and dying in fast forward, galaxies swirling like pinwheels, the cosmos evolving at an accelerated rate. It's like the ultimate meditation retreat, a place where you could theoretically step outside the rush of normal time and exist in your own peaceful bubble, watching the universe flow by like a gentle river. This isn't science fiction. It's a real consequence of how gravity affects space-time. Astronauts on the International Space Station, orbiting Earth at high speed in a slightly weaker gravitational field, age ever so slightly slower than people on the ground. It's an incredibly tiny effect. We're talking nanoseconds over months, but it's measurable and real. Near a black hole, this effect becomes extreme. Time dilation reaches its maximum. If you could orbit close to a black hole's event horizon for what felt like an hour to you, centuries or even millennia might pass in the rest of the universe. Of course, this is all theoretical. We can't actually visit a black hole. But there's something deeply soothing about knowing that such places exist, where time itself becomes fluid and flexible. where the relentless tick of the clock can finally slow down. In our everyday lives, we're often tyrannized by time, deadlines, schedules, the feeling that there's never enough time to do everything we want. But black holes remind us that time isn't the rigid, absolute thing it seems to be. It's flexible, relative. It flows at different rates depending on where you are and how fast you're moving. Time is more forgiving than we think. Black holes are cosmic recyclers. Here's a fact that might change how you think about black holes. They're not really holes at all, and they don't make things disappear forever. They're more like the universe's recycling centers. When matter falls into a black hole, it doesn't vanish into nothingness. It becomes part of the black hole, adding to its mass and energy. The black hole grows, evolves, changes. In this way, black holes are constantly transforming matter from one state to another. Think of it this way. A black hole is less like a cosmic trash can and more like a cosmic chrysalis. Matter goes in one form and eventually emerges in another. Nothing is destroyed. Everything is transformed. And here's the really fascinating part. According to physicist Stephen Hawking's theoretical work, black holes actually evaporate over time through something called Hawking radiation. It's an incredibly slow process. A typical stellar black hole would take longer than the current age of the universe to evaporate completely, but it means that black holes aren't eternal prisons. They're more like extremely patient transformers, slowly converting matter and energy back into the universe in a different form. The mechanism behind Hawking radiation is beautifully subtle. At the quantum level, empty space isn't really empty. It's constantly fizzing with pairs of virtual particles that pop into existence and immediately annihilate each other. But near a black hole's event horizon, something interesting can happen. One particle of the pair can fall into the black hole while the other escapes. The escaped particle becomes real Hawking radiation, and the black hole loses a tiny bit of mass in the process. This happening incredibly slowly, so slowly that we've never directly detected it. But over unimaginably long timescales, it means that every black hole will eventually return all of its mass to the universe as radiation. Nothing is truly lost. Everything is simply changed, rearranged, recycled. The atoms that fall into a black hole today might re-emerge, transformed beyond recognition, trillions of years in the future as a whisper of radiation spreading through an ancient, darkened cosmos. There's something comforting in that continuity, that endless cycle of transformation. The universe wastes nothing. Everything gets used, reused, transformed, and reborn in new forms. They create beauty we can see. Black holes themselves might be invisible. After all, even light can't escape them. But the regions around black holes are some of the most beautiful and luminous places in the universe. When matter spirals into a black hole, it forms what's called an accretion disk, a swirling disk of gas and dust that heats up to millions of degrees as it falls inward. This superheated material glows brilliantly, creating some of the brightest objects in the universe. Quasars. Quasars can outshine entire galaxies. A single quasar can be thousands of times more luminous than the entire Milky Way, even though it's powered by a region smaller than our solar system. Think about that for a moment. An object smaller than the distance from the Sun to Neptune, shining brighter than 400 billion stars combined. From across the universe, we can see these beautiful beacons, powered by the gentle, patient pull of black holes. They're like cosmic lighthouses, visible from billions of light years away, marking the locations of supermassive black holes in distant galaxies. And remember that famous first image of a black hole from 2019? The one from the Event Horizon Telescope that captured the black hole at the center of the galaxy M87? That glowing orange ring around the dark center? That's not the black hole itself. It's the light from the hot gas swirling around it, bent into a ring by the black hole's gravity. Some of that light comes from gas directly behind the black hole, but the black hole's gravity is so strong it bends the light around it, creating a ring of fire that we can see from 55 million light-years away. It's like the universe creating art, painting with light and gravity on a cosmic canvas. The black hole itself is invisible, but it reveals itself through the beautiful patterns it creates in the light and matter around it. That image, that first photograph of a black hole, represents the combined effort of telescopes from around the world, all working together to create an Earth-sized virtual telescope. It's one of humanity's greatest achievements, a moment when we finally saw with our own eyes something that had existed only in equations and theory. And what did we see? Not a monster, not something frightening, but something beautiful, a perfect circle of light, glowing warmly in the darkness, almost serene, almost peaceful. They're actually pretty hard to make. Despite what science fiction might have you believe, black holes aren't easy to create. You can't just make one in a laboratory, thankfully. You can't accidentally create one in a particle accelerator. They require specific, extraordinary conditions that are rare even on cosmic scales. The most common way black holes form is when a massive star, at least about 20 times the mass of our Sun, reaches the end of its life. After burning through all its nuclear fuel over millions of years, the star's core collapses in on itself in a catastrophic event called a supernova. Supernovae are among the most violent events in the universe. For a brief time, a single dying star can outshine an entire galaxy. The explosion is so powerful it can be seen from billions of light-years away. But if the remaining core after the explosion is dense enough, at least about 3 times the mass of our Sun compressed into a region the size of a city, it continues collapsing until it becomes a black hole. But here's the key. Our Sun will never become a black hole. It's simply not massive enough. When our Sun dies billions of years from now, it will swell into a red giant, then gently puff off its outer layers like a butterfly emerging from a cocoon, leaving behind a small, dense white dwarf star about the size of Earth. No black hole, no dramatic collapse, just a peaceful transformation. In fact, most stars in the universe will never become black holes. They'll live out their lives peacefully and fade away quietly. Black holes are reserved for only the most massive stars, the cosmic heavyweights. Out of every 1,000 stars born, maybe only 1 or 2 will be massive enough to end their lives as black holes. So as you rest tonight, you can take comfort in knowing that the sun that will rise tomorrow morning is going to keep shining steadily for about another 5 billion years, and it will never, ever become a black hole. It's simply too small, too stable, too comfortable in its current existence. Our sun is a patient, reliable star. It's been shining for 4.6 billion years already, and it will continue for billions more, providing light and warmth to whatever exists in the solar system during that time. It's one of the great constants in our lives. The sun rises, the sun sets, and it will continue doing so for longer than we can meaningfully comprehend. Supermassive black holes are galaxy guardians. At the center of almost every large galaxy, including our own Milky Way, there sits a supermassive black hole. These aren't the black holes formed from dying stars. These are giants, millions or even billions of times more massive than our sun. The one at the center of our galaxy is called Sagittarius A*, pronounced Sagittarius A star, and it's about 4 million times the mass of the sun. That sounds terrifying, but here's the beautiful truth. It's one of the reasons our galaxy exists in the form it does. These supermassive black holes act like anchors, holding galaxies together with their immense gravity. Stars orbit around them in graceful, predictable paths. The black hole provides a gravitational center, a focal point around which billions of stars can dance. Our sun, along with our entire solar system, orbits Sagittarius A*, once every 230 million years or so. We're currently about 26,000 light-years away from it, a safe, comfortable distance. We've been orbiting peacefully for billions of years, and will continue to do so for billions more. The last time we were in this particular position in our galactic orbit, dinosaurs were just beginning to dominate the Earth. The time before that, the supercontinent Pangaea was forming. The time before that, complex life was still confined to the oceans. Our solar system has made about 20 complete orbits around the galactic center since it formed. We're cosmic veterans, old hands at this galactic journey, and we've never had any problems. The black hole at the center is so far away that its influence on us is gentle, subtle, and entirely benign. There's something poetic about this. The thing that sounds most dangerous, a supermassive black hole, is actually helping to create order and stability in our galaxy. It's the heart around which everything else flows. It's the center that holds. Without supermassive black holes, galaxies might not form the beautiful spiral structures we see. They might not hold together as cohesive units. They might not create the stable environments where stars like our Sun can form and planets like Earth can evolve life. In a very real sense, we owe our existence to black holes. They're not destroyers, they're organizers. Not chaos, but order. Not danger, but stability. They might connect to other places. Now we venture into the realm of pure theoretical physics, but it's such a beautiful idea that it's worth contemplating as you drift towards sleep. Some theoretical models suggest that black holes might be connected to other regions of space through structures called wormholes or Einstein-Rosen bridges. In this scenario, a black hole might not be an endpoint at all, but rather a tunnel connecting one part of the universe to another, or even to another universe entirely. The mathematics of general relativity allows for these structures. The equations predict their existence, at least in theory. But here's where reality intervenes. These theoretical wormholes would be incredibly unstable. They would collapse almost instantly unless they were held open by some form of exotic matter with negative energy density. Something we've never observed and aren't sure even exists. And even if they could exist and remain stable, the journey through one would likely be fatal. The tidal forces would be extreme. The radiation would be intense. It would be less like a gentle tunnel through space and more like being caught in a cosmic blender. But as a thought experiment, as a dream to drift on, it's wonderful to consider. Imagine what we see as endings might actually be doorways. What seems like an impenetrable barrier might be a passage to somewhere entirely new. Black holes as cosmic gateways, portals, bridges between the known and the unknown. Some physicists have even speculated that every black hole might give birth to a new universe on the other side, creating a vast multiverse of bubble universes, each one spawned by a black hole in another universe. Our universe might have been born from a black hole in some parent universe. And every black hole in our universe might be creating new universes we can never see or visit. It's turtles all the way down, as the old saying goes. Or in this case, universes all the way down, each one containing black holes that spawn new universes in an infinite fractal structure of cosmic creation. Now, before you get too excited, we have no evidence that any of this is actually true. It's purely theoretical speculation, fun to think about but unproven and perhaps unprovable. But as a lullaby of ideas, as a landscape for the imagination to wander through as you drift towards sleep, it's beautiful. Whether it's true or not doesn't really matter for our purposes tonight. The possibility itself is soothing. The idea that the universe might be even more connected, more intricate, more full of hidden passages and secret routes than we ever imagined. The cosmos might be stranger and more wonderful than we know. They're patient teachers. Every black hole we study teaches us something new about the universe. They're natural laboratories where gravity is so strong that we can test the very limits of our understanding of physics. Black holes have taught us about the nature of spacetime itself, how it can bend, twist, and fold. They've helped confirm Einstein's theory of general relativity in the most extreme conditions imaginable. Every observation we make of black holes is another test of Einstein's equations, and so far those equations have passed every test with flying colors. They've shown us how matter behaves under incredible pressure and density. They've revealed the connection between gravity and quantum mechanics, hinting at a deeper theory that might unite these two fundamental forces of nature. They've demonstrated that information is more fundamental than we realized, leading to new insights about the quantum nature of reality. When we detected gravitational waves for the first time in 2015, ripples in spacetime itself, it was from two black holes spiraling into each other and merging 1.3 billion light-years away. That detection opened up an entirely new way of observing the universe, like suddenly gaining a new sense. Before 2015, we observed the universe through light, electromagnetic radiation in all its forms. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. But gravitational waves are something completely different. They're ripples in the fabric of spacetime itself, passing through everything, barely interacting with matter, carrying information about the most violent events in the cosmos. And we can detect them. We built instruments sensitive enough to measure distortions in spacetime smaller than the width of an atomic nucleus. We can hear the universe ringing like a bell when black holes collide billions of light-years away. Black holes don't rush to reveal their secrets. They've been around for millions or billions of years, and they'll be around for billions more. They teach us slowly, patiently, revealing their mysteries one discovery at a time. Each observation raises new questions. Each answer leads to deeper puzzles. There's something meditative about that pace. In our fast-paced world, where we expect instant answers and immediate gratification, black holes remind us that some things can't be rushed. Understanding takes time. Patience is rewarded with insight. The deepest truths reveal themselves slowly to those willing to wait and watch and wonder. The paradox that isn't scary. There's something called the black hole information paradox that puzzled physicists for decades. The basic question was, if information falls into a black hole, is it lost forever? This seemed to violate a fundamental principle of quantum mechanics that says information can never be truly destroyed. Imagine burning a book. Yes, the book is destroyed, but in principle, if you could track every atom, every photon, every particle of ash and smoke, you could reconstruct what the book said. The information isn't lost. It's just scrambled and spread out. Quantum mechanics says this is always true. Information is conserved. But what about a black hole? If you throw a book into a black hole, where does the information go? Can't escape, that's what makes it a black hole. So does it just vanish? Is it gone forever? For years, brilliant minds wrestled with this question. Stephen Hawking initially argued that information was indeed lost in black holes, which would mean quantum mechanics needed to be revised. Other physicists disagreed, leading to famous bets and decades of debate. It seemed like an irresolvable contradiction, a fundamental problem with our understanding of reality. Either quantum mechanics was wrong, or general relativity was wrong, or both were wrong. Something had to give. But more recent theoretical work suggests that information isn't lost at all. It's encoded on the black hole's event horizon, like data written on a cosmic hard drive, and eventually released back into the universe as the black hole evaporates through Hawking radiation. The paradox, it turns out, wasn't really a paradox at all. It was just something we didn't understand yet. Puzzle waiting to be solved. The universe wasn't contradicting itself, we just needed a better, more subtle understanding of how black holes work. And isn't that a comforting thought? The things that seem like contradictions, that seem impossible to reconcile, often aren't problems at all. They're just mysteries we haven't unraveled yet. The universe isn't broken or contradictory, it's just more subtle than we initially realized. As you lie here tonight, you might think about the puzzles in your own life that seem contradictory or impossible. The situations where you can't see a way forward, where everything seems irreconcilable. Maybe, like the black hole information paradox, they're not real contradictions at all. Maybe they're just waiting for the right perspective, the right insight, the right moment of understanding. The universe teaches us patience. It teaches us that apparent paradoxes often resolve themselves when we look at them from the right angle, with the right tools, with enough time and thought. Nothing is impossible. Some things just take time to understand. Spaghettification, a strangely gentle name. There's a term in astrophysics that sounds almost comically gentle. Spaghettification. It's what happens when the gravity near a black hole is so strong that it stretches objects into long, thin shapes, like spaghetti. The technical term is tidal forces, and it's the same effect that causes ocean tides on Earth. The moon's gravity pulls on the side of Earth, facing it more strongly than it pulls on the far side, because the near side is closer. This difference in gravitational pull creates the tides. Near a black hole, this effect becomes extreme. The gravity at your feet, if you were falling feet first into a black hole, would be much stronger than the gravity at your head, because your feet are closer to the black hole center. This difference in gravitational pull would gradually stretch you out, making you longer and thinner. Now, I'll be honest, the actual process wouldn't be pleasant if you experienced it. But there's something oddly soothing about contemplating it from a safe distance. Lying here in your bed, millions of light years away from the nearest black hole. And here's the interesting part. How quickly this happens depends on the size of the black hole. For a stellar mass black hole, the kind formed from a collapsed star, this stretching would happen relatively quickly as you approached. You'd be stretched thin well before you reached the event horizon. But for a supermassive black hole, the kind at the center of galaxies, you could actually pass through the event horizon without even noticing. The event horizon of a supermassive black hole is so large that the tidal forces at that point are relatively gentle. You could theoretically cross that cosmic point of no return and not feel a thing, at least not right away. The tidal forces would eventually become extreme as you fell further inward, but you could cross the event horizon itself in comfort, looking around at the strange sights of bent light and distorted space, unaware that you just passed the point of no return. It's a strange paradox. The bigger the black hole, the gentler the experience of falling into it, at least initially. The universe, once again, defying our expectations in subtle ways. We often think that bigger means more dangerous, more extreme, more violent. But with black holes, the opposite is true in some ways. The largest black holes are the gentlest, at least at their event horizons. It's the small ones you'd have to worry about if you ever got close enough. But again, you won't. You're safe here, far away, contemplating these cosmic oddities from the comfort of your bed. They're part of the cosmic ecosystem. Black holes don't exist in isolation. They're part of a larger cosmic ecosystem, playing an important role in how galaxies evolve and change over time. When black holes consume matter, they don't do it quietly. The material falling in heats up to millions of degrees, glows brightly, and often shoots out powerful jets of energy and particles at near light speed. These jets can extend for thousands or even millions of light years, punching through intergalactic space, pumping energy into the surrounding environment. This energy can trigger star formation in some regions while suppressing it in others. It can heat up vast clouds of gas, preventing them from collapsing to form new stars. It can change the chemistry of the space around it, enriching the interstellar medium with heavy elements. It can influence how galaxies grow, merge, and evolve over billions of years. In a very real sense, black holes are gardeners. They shape the cosmic landscape, pruning here, fertilizing there, creating the conditions for new stars to be born while preventing runaway star formation that would use up all the available gas too quickly. Without black holes, galaxies would look very different. They might form stars too quickly, burning through all their gas in a cosmic binge and then fading into darkness. Or they might not form enough stars, remaining as vast, cold clouds of gas that never ignite into the beautiful spiral and elliptical structures we see. Black holes help create balance. They regulate star formation. They shape galactic structure. They're an essential part of the cosmic machinery that makes galaxies work. Our galaxy has been shaped, at least in part, by the supermassive black hole at its center. The stars around you in the night sky, the very atoms that make up your body, exist in their current form partly because of the influence of black holes on galactic evolution. You are, in a sense, a distant descendant of black hole activity, part of the cosmic family tree that includes these mysterious, powerful objects. The iron in your blood might have been forged in a star that later collapsed into a black hole. The carbon in your cells might have been scattered into space by a supernova that created a black hole. You're connected to black holes in ways you might never have imagined. They're not alien, not separate, not other. They're part of the same cosmic story that includes you. The event horizon is actually peaceful. The event horizon, the boundary of a black hole, the point beyond which even light cannot escape, has a somewhat ominous name. Event horizon sounds like something from science fiction, doesn't it? A threshold to somewhere frightening or unknown. But from a certain perspective, it's actually one of the most peaceful boundaries in the universe. It's simply a region of space where gravity has become strong enough that the escape velocity exceeds the speed of light. Escape velocity is the speed you need to break free from a gravitational field. For Earth, it's about 11 kilometers per second. For the Sun, it's about 618 kilometers per second. As you get closer to more massive objects, the escape velocity increases. At the event horizon of a black hole, the escape velocity reaches exactly the speed of light. And since nothing can travel faster than light, nothing can escape from beyond that point. But here's what's remarkable. There's no wall there, no barrier, no physical edge, no sign that says point of no return. If you could approach a supermassive black hole's event horizon, you wouldn't see anything special at that exact location. Space wouldn't look different. The stars would still be visible, though distorted. You could pass through it as easily as passing through an imaginary line like the equator. The event horizon is more of a mathematical concept than a physical thing. It's a point of no return, yes, but it's a gentle one. A threshold you cross without fanfare or drama. You'd only realize you'd crossed it when you tried to turn around and found that every direction you could travel led further inward. In our lives, we cross event horizons all the time, don't we? Points of no return where we can't go back to how things were before. A decision made, a word spoken, path chosen, a relationship ended or begun, a move to a new city, career change, a child born. And often, in the moment, these crossings are quiet, unremarkable. It's only in retrospect that we realize we've passed through something significant, that we've crossed an invisible boundary into a new phase of life. Black holes remind us that the most profound boundaries are often invisible, unmarked, and peaceful in the moment of crossing. It's only later, when we look back, that we realize we've passed a point of no return. And that's okay. Life is full of event horizons. We cross them all the time. Some we choose, some choose us. But each one takes us somewhere new, somewhere we couldn't have gone without crossing that invisible line. They glow in ways we're only beginning to see. For a long time, we thought black holes were completely invisible, the darkest objects in a dark universe. After all, if light can't escape them, how could we ever see them? But then we discovered that black holes emit something else: Hawking radiation. It's named after Stephen Hawking, who predicted in the 1970s that black holes should emit a very faint glow due to quantum effects near the event horizon. The mechanism is subtle and beautiful. At the quantum level, empty space isn't really empty. It's constantly fizzing with pairs of virtual particles that pop into existence and immediately annihilate each other. like cosmic foam. Near a black hole's event horizon, something interesting can happen. One particle of the pair can fall into the black hole while the other escapes. The escaped particle becomes real Hawking radiation, carrying away a tiny bit of the black hole's mass energy. The black hole shrinks, ever so slightly, with each particle that escapes. This radiation is incredibly faint, so faint that we've never directly detected it from an actual black hole. A typical stellar mass black hole emits Hawking radiation with a temperature of just a few 10 millionths of a degree above absolute zero. That's colder than the cosmic microwave background, the ambient temperature of space itself, which means the black hole is actually absorbing more radiation from its surroundings than it's emitting. So from our current perspective, black holes are getting colder and larger, not smaller. They're still growing, still feeding, still accumulating mass faster than they lose it through Hawking radiation. But here's the beautiful part. The universe is getting colder too. As the universe expands, the cosmic microwave background cools down. Eventually, in the unimaginably distant future, the universe will be colder than the Hawking radiation of even the largest black holes. And when that happens, black holes will begin to evaporate. Slowly, patiently, over timescales that make the current age of the universe seem like a brief moment. A stellar mass black hole will take about 10 to the power of 67 years to evaporate. That's a 1 followed by 67 zeros. The largest supermassive black holes will take even longer, perhaps 10 to the power of 100 years or more. To put that in perspective, the universe is currently about 13.8 billion years old, which is about 10 to the power of 10 years. The timescales for black hole evaporation are so long that comparing them to the current age of the universe is like comparing the age of the universe to a single second. But eventually, given enough time, more time than we can meaningfully comprehend, every black hole will evaporate. They'll shine themselves out of existence, slowly, patiently, particle by particle, returning their mass to the universe as a faint whisper of radiation. It's the ultimate long goodbye, a reminder that even the things that seem eternal and unchanging are, in the end, temporary. Everything in the universe is just passing through, existing for a while before transforming into something else. Black holes teach us patience on cosmic scales. They remind us that nothing lasts forever, but not forever can still mean an incomprehensibly long time. They show us that endings can be gentle, gradual, peaceful, a slow fade rather than a sudden stop. They make time travel theoretically possible. Here's a fun thought to drift on as you settle deeper into your pillow. The extreme space-time curvature around rotating black holes creates some very strange effects. According to general relativity, it might be theoretically possible to use the space-time around a rotating black hole to travel through time. A rotating black hole, called a Kerr black hole, named after the physicist Roy Kerr who first described their properties mathematically, has some unusual features that non-rotating black holes don't have. When something spins, it drags space-time around with it. You can think of it like a ball spinning in honey. The honey near the ball gets pulled along with it. Around a rotating black hole, space itself gets dragged along with the rotation, creating a region called the ergosphere where it's impossible to stand still. You have to move with the rotation whether you want to or not. Inside the event horizon of a rotating black hole, the structure becomes even stranger. There's another boundary called the inner event horizon, and beyond that, theoretically, a region where the normal structure of spacetime breaks down entirely. Some solutions to Einstein's equations suggest that you could potentially enter a rotating black hole at just the right angle, pass through this inner region, and emerge elsewhere, or elsewhen, perhaps in another time, another place, another universe. The equations allow for the possibility of closed time-like curves, paths through spacetime that loop back on themselves, allowing you to arrive back at the same point in space and time where you started, or even earlier. Now, before you get too excited about building a time machine, there are massive problems with this idea. The trip would likely be fatal, the tidal forces would be extreme, the radiation would be intense, and we have no idea if the inner structure of a rotating black hole is actually stable enough to traverse. More fundamentally, we're not even sure if these exotic solutions to Einstein's equations represent real physical possibilities or just mathematical curiosities. The equations allow for all sorts of strange things that might not actually exist in nature. But just as a thought experiment, just as a dream to carry into sleep, the universe might be even stranger and more interconnected than we imagine. Time might not be as linear as it seems. The past and future might be more accessible than we think. The strict arrow of time that seems so absolute might be more flexible in extreme conditions. Whether it's true or not doesn't matter for our purposes tonight. The possibility itself is soothing. The idea that time is more fluid, more navigable, more forgiving than we usually assume. Maybe the moments we regret could be revisited. Maybe the futures we fear could be avoided. Maybe time is less like a highway with one direction and more like an ocean we're learning to navigate. It's a comforting thought to drift on. The idea that reality might be more flexible, more full of possibilities than our everyday experience suggests. The calm at the center, at the very heart of a black hole, according to our current understanding, lies the singularity, a point of infinite density where all the black hole's mass is concentrated. Now, infinite density sounds dramatic and frightening, but here's an interesting thing to consider. We don't actually know what's there. Our current theories of physics break down at the singularity. The math stops working. We reach the limits of what we can describe with our current understanding. General relativity predicts the singularity, but general relativity also tells us that it breaks down under those extreme conditions. It's like a map that says, "Here be dragons." The theory itself admits it can't tell us what happens in that region. Some physicists think there might not be a true singularity at all, that quantum effects we don't yet understand might prevent the formation of a point of infinite density. The center of a black hole might be something else entirely. A quantum foam, a bounce into another universe, a region where time and space swap roles, a place where the fabric of reality itself is fundamentally different from anything we can currently imagine. We simply don't know, and there's something peaceful about admitting that. At the heart of one of the universe's most extreme objects, there's a mystery we haven't solved, a question we can't yet answer. It's okay not to know everything. It's okay to encounter limits to our understanding. The universe is under no obligation to make sense to us, and yet we keep exploring, keep questioning, keep wondering. The singularity at the heart of a black hole is like the mystery at the heart of existence itself. We can circle around it, study it from different angles, develop better and better theories, but ultimately, some things remain beyond our complete grasp, at least for now. And that's not frightening. That's beautiful. That's what keeps the universe interesting. There are still mysteries to solve, still questions to answer, still frontiers to explore. We don't know everything, and that means there's still wonder left in the world, still discoveries waiting to be made, still surprises the universe has in store for us. As you drift toward sleep, you can rest in that not knowing. You don't have to have all the answers. The universe doesn't have all the answers, and that's perfectly fine. Some mysteries are meant to remain mysteries, at least for a while longer. They're surprisingly common, yet perfectly spaced. Here's something that might surprise you. Black holes are not rare cosmic oddities. They're actually quite common throughout the universe. Our galaxy alone probably contains about 100 million stellar mass black holes, the remnants of massive stars that lived and died over billions of years. That sounds like a lot, and it is. But remember, our galaxy contains somewhere between 100 and 400 billion stars. So black holes make up a tiny fraction of what's out there, maybe one black hole for every few thousand stars. And they're spread out over vast distances. The Milky Way galaxy is about 100,000 light-years across and contains most of its stars in a disk about 1,000 light-years thick. That's a volume of space almost incomprehensibly large. Those 100 million black holes are scattered throughout that enormous volume, each one typically separated from its neighbors by many light-years of empty space. The nearest known black hole to us is about 1,600 light-years away. The next nearest might be twice that far. They're not clustered together. They're spread out, each one drifting through space on its own trajectory, minding its own business. It's like living in a large country with millions of other people. Yes, there are many people around, but if you stand in the middle of a quiet field, you might not see another person for miles. Space is big enough that even common objects are separated by unimaginable distances. So yes, black holes are common in an absolute sense, but the universe has given us plenty of room. You're safe here. The black holes are out there, doing their thing, playing their role in the cosmic dance, but they're not anywhere near you. They're not coming toward you. They're just existing peacefully in the vast expanses between the stars. You can rest easy. The universe, for all its black holes and mysteries, is mostly empty space. Quiet, dark, peaceful, and you're safe in your small corner of it, on your small planet, in your warm bed, surrounded by the gentle night. The dance of binary black holes. Sometimes, two black holes find each other in the vastness of space. It's rare, but it happens. Maybe they were born from a binary star system, two massive stars orbiting each other that both collapsed into black holes. Or maybe they encountered each other in the crowded center of a galaxy, where millions of stars and stellar remnants swirl around the central supermassive black hole. When this happens, they begin a slow, graceful dance. They orbit each other, bound together by gravity, spiraling closer and closer over millions of years. As they orbit, they emit gravitational waves, ripples in the fabric of spacetime itself, and these waves carry away energy. As the binary system loses energy, the orbit shrinks, and the black holes spiral closer together. Slowly, patiently, for millions of years, they dance together, two partners in an ancient cosmic waltz, drawing imperceptibly closer with each orbit. Then, in the final moments, the pace quickens. The orbit shrinks rapidly. The black holes spiral faster and faster, orbiting each other hundreds of times per second, until finally they merge. The merger happens in a fraction of a second. Two black holes become one. The collision releases more energy than all the stars in the visible universe are emitting at that moment, but it's all released as gravitational waves, not light. It's a silent explosion, perceptible only to detectors sensitive enough to measure the ripples in spacetime. We've detected these mergers now, thanks to instruments like LIGO and Virgo. We can hear the spacetime ripples washing over Earth as these distant black holes complete their final dance. The signal sounds like a chirp, a rising tone that sweeps up in frequency and amplitude as the black holes spiral together, then cuts off abruptly when they merge. There's something beautiful about that image, isn't there? Two massive objects, dancing together for millions of years, gradually drawing closer, until finally they become one. A cosmic romance playing out on the grandest scale imaginable. It's a reminder that even the most massive, powerful objects in the universe don't exist in isolation. They interact. They influence each other. They find companions. They dance together in ways that ripple across the cosmos. In the vastness of space, across the gulfs of time, connections form. Partnerships develop. Even black holes, it seems, don't have to be alone. The gentle conclusion. And so, we come to the end of our journey through the calm, mysterious world of black holes. These objects that sound so frightening, so alien, so dangerous, turn out to be patient teachers, cosmic architects, and ancient keepers of secrets. They're far away, engaged in their slow dances through space. They anchor galaxies. They recycle matter. They teach us about the nature of time and space and gravity. They preserve history in ways we're only beginning to understand. They connect us to the deep past and the distant future. Most importantly, they remind us that the universe is more subtle, more beautiful, and more interconnected than we often realize. The things that seem like endings might be transformations. The things that seem empty might be full of possibility. The things that seem frightening might be, when you really understand them, sources of wonder and peace. Black holes teach us patience. They show us that time is flexible, that information is preserved, that nothing is ever truly lost. They demonstrate that the most profound boundaries are often invisible and crossed without fanfare. They remind us that we don't have to know everything, that mysteries are okay, that the universe is still full of wonders waiting to be discovered. As you close your eyes now, you can rest easy. The black holes are out there, billions of them throughout the universe, quietly doing their work. They've been there for eons before you were born, and they'll be there long after you wake up tomorrow morning. They're not coming for you. They're not a threat. They're just part of the universe, part of the cosmic ecosystem that makes existence possible. They're distant lighthouses in the dark, markers of where gravity grows strong, places where the universe reveals its deepest secrets to those patient enough to study them. Sleep well, knowing that the universe, with all its black holes and mysteries, is exactly as it should be. Everything is in its place. Everything is following the gentle, patient rules of physics that have governed the cosmos for billions of years. And you, here in your bed, are safe and sound, a small part of an infinite cosmos, connected to everything, from the smallest quantum particle to the largest supermassive black hole, through the simple fact of existence. You are made of star stuff. You are the universe contemplating itself. You are a brief, beautiful moment in an ancient, ongoing story. Rest now. Dream of gentle cosmic dances, of time flowing like honey, of singularities that are simply mysteries waiting to be understood, of event horizons crossed peacefully, of binary black holes waltzing through eternity. The universe is vast and strange and beautiful, and you are a part of it. You belong here. You are connected to it all, to the stars, to the galaxies, to the black holes themselves, through the atoms in your body and the consciousness that contemplates these cosmic wonders. Everything is connected. Everything is one. And in that oneness, there is peace. Good night. Sleep well. And may your dreams be filled with the peaceful, infinite wonders of the cosmos. The black holes are singing their deep, slow songs in the darkness. The stars are shining their ancient light. The universe is unfolding according to its timeless patterns. And you are here, safe and warm, part of it all. Rest now.